Good afternoon. So today we will introduce the concept of a series, or to be more specific, we're going to begin this chapter with infinite series with positive terms. This is the lesson that I like to take my time to go over it, and you should do the same. If you feel like it, take the equivalent of 2 lecture meetings to go over the whole lesson, because it's extremely important to really understand the basic concepts the way they are defined. I can't stress this enough. If you actually put all the effort you can in the beginning to understand really the definitions and the main idea behind infinite series, everything else in the chapter is going to be pretty easy, because all we're going to do after today's lesson is essentially going over types of series, some examples, how we figure out when they converge or not, which is to say we're going to see what we mean by that immediately. And then some applications of series, because obviously we do these things because they are good for other useful things later. The difficulty with concepts like this is that people tend to again skip the basic math definition and try to use intuition, and intuition often is misleading. So roughly speaking, an infinite series is basically another name for an infinite sum. And for example, the intuition can already be misleading if you try to figure out what could that mean if you have a sum of positive terms that we keep on adding them indefinitely. And by the way, notice the reason we needed sequences, because to refer to an infinite sum, I need to refer to these terms in the sum with some sort of indexed variables like a1, a2, a3, and so on, right? So if you can think of an infinite series like the sum of the elements of a sequence. So you have an infinite sequence. What happens if I add all of the elements, like all infinitely many of them? And the intuition can fail because you may think that, well, didn't you just say that the sequence is positive? So, if I add up positive terms indefinitely, don't I just go to higher and higher values, basically to infinity? And if you really think very, very carefully, and especially if you maybe think a little bit about improper integrals, you may see that the answer is not that obvious, and that the answer can actually be no. It may not lead to an infinite quantity, even though you add infinitely many positive numbers. Because improper integrals, remember, are of 2 types, convergent or divergent. And in the convergent case, you still dealt with surfaces that were infinite in size, if you want, in dimension, right? Infinite length, for instance, right? I mean the region below a graph that would extend indefinitely to the right. We can illustrate also the concept why an infinite sum of positive quantities can be a finite number with another very useful and intuitive example that I like to provide right now. And let's take the time to do this little game. So let's say you have a square of size 1, not of size 1, of side 1, right? So the length of each side is equal to 1. And I'm going to actually compute or add up pieces of the areas of this square in a certain pattern. What I'm going to do, I'm going to basically add half of the remaining area at a time. So I'm going to keep on adding half of the remaining area at a time. So for example, I'm going to start by adding half of the area given by this rectangle. So if I split this into 2 equal parts, then the area is going to be obviously 1 times 1 over 2. 1 times 1 over 2, that's going to be there, because the width is going to be 1 over 2, and then the side is still 1. And I'm going to continue this process. So the remaining area, I'm going to split it into 2 again. Okay, so now it's 1 over 2 times 1 over 2. And then the remaining area, I'm going to split it into 2 again. So let's see what happens now. So this is going to be 1 over 2 times 1 over 2 divided by 2, which is really 1 over 4. But 1 over 4 is really 1 over 2 times 1 over 2. I just wanted to see the pattern here. So this little rectangle that I'm basically emphasizing has the sides 1 over 2 and, excuse me, 1 over 2 and 1 over 4. So when you multiply to find the area, that's going to be 1 over 8. And again, if I move on, okay, continue with this game, the next one will be 1 over 2 multiplied 4 times. So it's going to be 1 over 2 to the power of 4. So let me write it again as powers of 2, right? So the first half was 1 over 2, the area of the first half. The next one was 1 over 2 squared. The next one was 1 over 2 thirds. Then 1 over 2 to the power of 4. If I split it again into 2, the next one will be 1 over 2 to the power of 5. And I keep on going. And it should be pretty obvious that no matter how many terms I add by keep on doing this game, by adding half of the remaining part, so on and so forth, although this basically is an infinite sum, intuitively, clearly this is going to approach the area in the limit, is going to approach the area of the square, which we know is equal to 1. So what I mean is that you add infinitely many positive quantities, yet you don't get outside of the square. And in fact, in the limit, you fill in the square, basically. So you're going to basically find out the area of the square, which is got to be 1, because we know it's 1 times 1. So basically what I just told you here is a very basic geometric intuitive proof, if you want, that you can have an infinite sum, right? Keep on adding positive quantities like this, that leads to a finite number. We have to basically define carefully what we mean this equal to 1, because we still didn't define yet what we mean by adding infinitely many numbers. That's another issue here. We know how to add finitely many numbers, but for infinitely many numbers, we need to give a formal definition, a formal math definition. But intuitively, such definition should exist because of this type of process that obviously suggests the limit is equal to 1 for this infinite sum. So I hope I convinced you that infinitely many numbers added together, even if they're positive, can end up with a finite number, and that'll be the big question. And on the other hand, it's pretty obvious when that doesn't happen. If I told you that I'm gonna add, let's say, powers of 2. So if I say I'm gonna add 2 and then 2 first and then 2 second, 2 first, 2 second, 2 thirds, 2 to the power of 4, 2 to the n. Again, it wouldn't be far-fetched. You won't be too far hard-pressed to not realize that this goes to infinity. It's not going to approach a finite number because what you add up is much bigger than what you had before. You keep on increasing the size of what you add. There's no chance of this infinite sum to be confined. So no chance to be confined inside some sort of boundary, like in my square example. So therefore, the main question in this chapter is, when does it approach a finite number, such an infinite series, when it doesn't, and the implication of this, of the answer to these questions. So with that in mind, let's stay tuned for the next page for a formal definition of series. So before we define a series, let's go over one notation first of all. So an infinite sum, which we can write it in terms of a sequence, right? I mean, by adding the terms of a sequence, we can write it in a shortcut format using the sigma notation, summation from 1 to infinity of an. So we're going to use this symbol from now on. And then the question is, how do we define whether this infinite sum has a limit or not, or exists or not? So does this sum exist? In other words, is it a finite real number? So for such a sum to exist, we do the definition basically of this of the infinite sum, basically of the summation of an infinitely many numbers, via limits of sequences, but sequences of partial sums. Because remember, when we did this intuitive process on the previous page, we kept on adding one additional term and basically figure out whether we approach a finite number or not. So in the previous page, we started with 1/2. Then we said, okay, if I add another half of the remaining part, then I have that. Then what if we add another piece of the remaining, another half of the remaining part? Then we have this. So if you look carefully, if my terms of the series were 1/2, 1/2 squared, and then 1/2 to the n at some point here, right? The next one will be 1/2 to the power 3, and so on. To figure out whether there is a limit or not, we basically looked at what happened to the values of these so-called partial sums. Okay, partial sums because you look at finitely many terms and you keep on adding an additional term to see if there is a trend, or in other words, there's a limit to those partial sums. So in general, the partial sums of a series given generically as summation from 1 to infinity of an are given by S1 equals A1. So they form a sequence in themselves, right? So the first partial sum is the first term. The second partial sum will be the first two terms added together. The third partial sum is A1 plus A2 plus A3, and so on. The nth partial sum is just the sum of the first n terms, and you keep on going. So each series has attached to it the so-called sequence of partial sums. So one of the most important things I want to mention here is to never confuse the sequence that form the terms of the series, right? So that means the sequence, A1, A2, An that form the infinite sum, with the sequence of, so whenever they confuse the sequence that form the terms of the series with the sequence of partial sums, which is given over here, right? The sequence of partial sums are, like the name implies, these summations involving the terms of the sequence. Many theorems of convergence of a series are in terms of what happens to the terms of the series. And for example, if I say that the sequence itself that forms the series converges, let's say if I say something about An, that doesn't mean that the same is true about the sequence of partial sums, Sn. So with this definition in mind of the sequence of partial sums, now we can formulate that the limit, the existence of an infinite sum. So we say that a series from 1 to infinity, summation of n from 1 to infinity of An, converges if the limit of its partial sums exists and is finite. So basically we can write essentially the equality sign between the summation from 1 to infinity of An with a limit as n goes to infinity of the partial sums. If this limit exists, then this is basically the sum of the series. So the sum of the series is this limit. So if the limit exists. So we can only say what an infinite sum is in terms of equal to a number insofar this precise limit exists. If it doesn't, then the series is divergent. So the summation of n converges if the limit of the partial sums, which again remember stands for a1 plus a2 plus ... an. If this limit exists, then the summation of an exists. I mean the sum of the series exists. Otherwise, we say that the series is divergent. So let me say it one more time before we move on to some examples and basic properties before we move on with other things. From this point on, try to think everything in terms of the strict definition we have here. Often we cannot use the intuition in terms of whether the series converges or not. And the answer is always given by the computation of this limit or by theorems which bypass this limit. So we're going to learn, for instance, properties and theorems which will allow us to figure out whether the series converges or not without the need to actually compute the limit, which sometimes it's a hard problem in itself. But this is the notion of an infinite sum via essentially a limit of a sequence, which is the reason why we went over limits of sequences in the previous lecture. So with that in mind, let's move on with a couple of examples, and in particular we're going to start with the easiest property in this chapter, which is essentially a test to see if the series diverges. One of the most misused tests actually in the beginning, but if you pay attention, then it's very easy. And stay tuned for the next page. All right, so let's discuss what is called in the literature the divergence test. Remember my previous example when I stated that if I add terms that are obviously bigger and bigger, it doesn't take too much guessing to realize that this is basically a divergent series. You keep on adding higher and higher values. So this is essentially the easiest test that excludes the obvious case in which a series diverges. Whether it converges or not, that's a different question. But the obvious case in which it's divergent, if it's what you add up, if you keep on adding up stuff that doesn't get smaller and smaller, but in fact, like in this case, like in this extreme case, gets higher and higher, clearly that summation will diverge. So the formulation of the divergence test simply states that if a sequence that is part of the terms added to the series, right? So if limit of an as n goes to infinity is not equal to 0, which is to say is not gonna be with it's not involving the terms that go that increases basically. So if it doesn't go to 0, if it don't get smaller, if these terms don't go smaller and smaller, then the infinite series involving these terms is divergent. It is a one-directional statement. If the left happens, the right happens. The converse is not true. And I'll go over a couple of examples immediately so that you won't confuse the notion. One of the common mistakes is people state that if an approaches 0, then summation of an is convergent. So this statement is not true, right? As I'm going to show you immediately with a couple of examples. So make sure when you read these tools, I mean these theorems that deal with convergence or divergence of series, you read it carefully and don't conclude what the statement doesn't say. The statement simply states a criteria for divergence. It never tells you when the series converges or not. It just tells you that under some condition, under a certain condition, which is limit of an not equal to 0, under that condition, then the series will diverge. So so basically, if I look, for example, at summation from 1 to infinity of let's say 5 to the n over 3 to the n plus 1, we learn about limits of functions, right? The first thing to do is to try the divergence test, because if this test applies, you don't need to use any fancier methods of figuring out the convergence or not. It's a very quick test. For the infinite sum to exist, we will need this term inside the series to converge to 0. Does it or does it not? Because if it doesn't go to 0, the divergence test tells me that the series is divergent. So the first thing to do is to take separately the sequence that forms the series. This leads to a comparison. It's an infinity over infinity case. 5 to the n over 3 to the n. That's 5 over 3, which is greater than 1 to the n. And that's going to be infinity. So this obviously is not equal to 0, which means the summation given here, the infinite sum, is divergent. Here's another example. Let's say you have summation from 1 to infinity, 2n over 5n plus 1. I'm looking at the limit of the term in the sequence. This leads to the ratio of the dominating terms. Remember, we discussed this in the previous lecture. The limit is 2 over 5. It's not equal to 0. Therefore, the series itself is divergent. Again, notice I'm not talking about the sequence. The sequence itself has a limit. It's 2 over 5, but it's not 0. And as the divergence test implies, that means the series that adds up those terms in the sequence is divergent. Again, very important to realize that if an goes to 0, the divergence test says nothing. And I'm going to show you, perhaps with a different example on the next page, two different cases. So if an goes to 0, summation of an from 1 to infinity may or may not converge. So I'll show you examples of both. In fact, one example of convergence you already saw, right? So remember when we added up the those pieces of the square, 1 over 2, 1 over 2 squared, and so on, right? In the shortcut notation, that was summation from 1 to infinity, 1 over 2 to the n, and we showed intuitively this is basically convergent to 1, right? And see, this is one of those cases in which the limit of the sequence that forms the series itself is equal to 0, right? The limit as n goes to infinity of 1 over 2 to the n, that's equal to 0. On the other hand, on the second page, I'm going to show you another example in which the limit is 0, yet the series diverges. So again, so far, just based on the divergence test, the fact that an goes to 0 tells us nothing. Either of the two is possible, convergent or divergent. So stay tuned for the next page with an example related to this. All right, so take a look at this following famous example. It's summation of 1 over n, basically. So I'm looking at 1 plus 1 over 2 plus 1 over 3 plus ... 1 over n and so on. By the way, in terms of how you write it down, that's like summation from 1 to infinity, 1 over n minus 1. Because, excuse me, what am I saying? No, 1 over n. I was thinking about something else, actually. Let me actually write it down nicely here. So summation from 1 to infinity, 1 over n, right? So remember, according to our definition, for this to converge, we will need the limit of the partial sums to converge. So the question is, what is the limit of the sequence of the partial sums, the first n terms added together. And if you actually check this summation on the computer by keep on adding the terms, it can be misleading because it may look like it's approaching a number. Although if you, now you can add thousands and thousands of terms here quickly with the computer algebra system, and you'll see that actually the answer is not convergent. And it's counterintuitive somehow because, you know, just like in the previous case, you still add quantities that go to zero. So notice if I look at the limit of the sequence itself, that's still zero, just like 1 over n squared, like in the previous case. So it's not like what you add doesn't get smaller and smaller. But the thing is, it doesn't get small enough with each additional term. That's what makes it convergent. And in this case, it's not small enough what you add on each additional term. And we can basically illustrate this with what we're going to call later integral test, but right now I'm going to show you an intuitive argument from improper integrals. Take a look at the graph of the function 1 over x for x greater than or equal to 1. If I sketch the graph of this function, which looks like that, and so this is the point x equals 1, and from 1 to infinity, right, let's actually do some sort of approximate integration basically. So I'm going to do a partition of length 1, so that, let's say this is equal, this is 2, then followed by 3, 4, 5, and so on. And I'm going to basically approximate the integral by overlapping squares, rectangles, with the left endpoint for each interval in the partition as an intermediate point. So remember, if I choose, for example, if I look at the first piece of the interval, I can choose any point to be the point where I raise the perpendicular to construct the the approximating rectangle. But I'm going to choose always the left endpoint. So here I'm going to choose the the point at x equals 1, raise the perpendicular, and I'm going to write down the area of the rectangle here, which is going to be 1 times 1, right? So the distance between 1 and 2, and the height is 1. Then on the second interval, I'm going to do the same thing, raise the perpendicular over 2, and then compute the area of that rectangle. That's going to be 1 over 2, the height, right, times 1. And then same thing between 3 and 4, I'm going to raise the perpendicular over 3, and that's going to be 1 over 3, right? The value of the function at 3 is 1 over 3, right? And this is just 1 over 2, and so on, times 1. Then it's going to be 1 over 4 times 1, this rectangle. Keep on adding up the terms like that. So at some point it's going to be 1 over n times 1 plus ... The way I chose this Riemann sum, this is nothing but a Riemann sum, but for the improper integral basically. The way I chose this Riemann sum, that's going to be an overestimation of the integral between 1 and infinity, right? Because I keep on adding these corners above the actual area under the graph. So let's emphasize the area under the graph here, which is given by the integral from 1 to infinity. So it's clear that this Riemann sum is got to be greater than the integral from 1 to infinity of 1 over x dx. So on the left, you have essentially the infinite sum, and on the right hand side you have this improper integral, which is natural log of x between 1 and infinity. When I pass the limit on the upper border, that's going to be infinity, ln of 1 is 0, so that's infinity. So intuitively we can see that this infinite sum, right, of adding 1/2, 1/3, 1/4, 1 over n is got to be greater than something that actually approaches infinity. Now what's greater than infinity? Nothing but infinity. So We see therefore that the summation from 1 to infinity of 1 over n is divergent, although as you saw in the previous case, the summation of 1 over n squared was convergent. This is a classical example that you have to keep in mind so you won't make a mistake using the divergence test. The sequence in the series going to 0 tells you nothing. It can be convergent, as you can see here in the 1 over n squared case, or it could be divergent, as you can see in summation of 1 over n. Obviously, that's the reason we have an entire chapter with criteria of convergence in other cases. The divergence test is still important because it's the first check. When you look at the series, the first thing to do is to take the limit of that sequence, because if it doesn't go to 0, therefore you can conclude divergence. But if that doesn't happen, then you move on to other theorems that deal with the convergence or divergence later on. So stay tuned for another part of the lecture, which introduces a one of our first series to deal with, the so-called geometric series. So one of the first series to deal with, a very important one, all the same, is the so-called geometric series, which basically is identified by two real numbers, a and r. A denotes essentially the first term in the series, and then the terms in the series that are added together are obtained by multiplying by r the previous term. So basically you have a, the starting point, or the seed if you want, and then r is called the ratio of the geometric series, and the later terms that are added together are obtained from the previous ones and then multiplied by the ratio. So a plus r squared, the next one will be ar third, arn, r to the n, and so on. Now, because it's convenient to write the summation from 1 to infinity, this infinite sum is typically denoted by the summation from 1 to infinity a r to the n minus 1. Now, if this n minus 1 is confusing, notice that the first exponent of r would be 0. You can think of a as a times 1 or r to the 0. In some cases, depending on the situation, you can have 0 as a starting value of n, in which case you can write the series as summation from 0 to infinity as a r to the n. The actual first index is not strictly important. It's not that important. You can make it to be 0 or 1. It's just a matter of habit to an extent. Because most of the series are from 1 to infinity, I'm going to, as much as possible, I'm going to use this version from 1 to infinity. But notice you can have other versions here. The important thing is when you plug in the first value of n, to render the exact terms that you will see in the series. So the first term should be ar to the 0. So therefore, if you start from 1, then you have to put n minus 1 as the exponent so that it becomes 0 with the first value of n. So the question is, when does this geometric series converge or diverge? Obviously, that's going to be the overall question we're going to address throughout this chapter. Is it convergent or divergent? In general, I'm going to show, or I'm going to state these results without proof. In some cases, it's useful to go over the proof just to reinforce the definition of convergence. And this is one of those cases in which we could do that. So remember, whether the series converges or diverges is decided by the sum of by the sequence of partial sums. You look at the sequence made by the partial sums. So basically Sn will be the sequence, the first n terms added together. So this goes all the way up to ar to the n minus 1 if you're careful here, right? Because the counting starts from r to the 0. So the first n terms go from 0 to n minus 1. So whether the series converges or not depends on whether the limit as n goes to infinity of Sn exists or not. So we're going to have to somehow compute this limit, or to figure out when this limit exists or not. So we could do this with a little trick. We have, let's write down Sn again. So a plus ar plus a r to the n minus 1. I'm going to multiply by r the entire summation, left and right. So r times Sn equals a times r. So each exponent increases by 1 unit, if you notice carefully. So a times r, the second one is a r squared. Then what used to be arn minus 2 now becomes arn minus 1. And then finally, the last one now is going to be arn. And once again, Sn, the original Sn was a plus ar plus dot 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 all the way up to arn minus 1. Make sure you pause to catch up all these computations. All right, so if you look carefully now, if I subtract the two, to be more precise, if I subtract Rsn from Sn, then I'm going to basically have a huge cancellation here. All these terms from AR to ARN minus 1 will cancel out. So Sn minus Rsn, these two will cancel, ends up being A minus AR to the n. So it's one of those few rare cases in which we could actually compute what the partial sum is equal to. That's a rare event. Typically, we can pull out A here. Typically, we can't really do this computation, to actually find the exact value of Sn, which is the reason why we need this convergence theorem usually. And at this point, before I actually divide Sn, let's see actually what happens when r is equal to 1. Right, so actually we're going to treat this case separately because we can divide by 0, right? I have to take from this point on r not equal to 1. So I could divide by 1 minus r. So that gives me Sn equals a times 1 minus r to the n over 1 minus r. So it all boils down to finding the limit of Sn, which is the same as the limit of a 1 minus r to the n over 1 minus r. So fortunately, it boils down to the limit of r to the n. So actually, let's write down over here a basic result from the limits of sequences. So if you have a real number to the power n, and you already know this intuitively, but generally speaking, the limit of r to the n is gonna be 0 if r is between minus 1 and 1. So if it's between minus 1 and 1, the limit is 0. R equals 1, the limit will be obviously 1. 1 to the n is 1. So it's going to be 1 if r is equal to 1. It's going to be infinity if r is greater than 1. And the limit doesn't exist if r is less than minus 1. It's like minus 3 to the n. It goes to plus minus infinity essentially. Because minus 1 to the n oscillates between minus 1 and 1. And we're going to deal with r equals 1 separately. But notice that for the series to be convergent, we actually need r between minus 1 and 1. So that's the case. Let's see, because if r is equal to 1, r is equal to 1, I have to do this case separately. And then the other case, the limit doesn't exist, is infinity or doesn't exist. So if r is between minus 1 and 1, then the limit of a 1 minus r to the n over 1 minus r is going to be a 1 minus 0 over 1 minus r. We just passed the limit over that expression. So that's going to be a over 1 minus r. In all other cases, if r greater than 1 or less than minus 1 is going to be divergent. If it was to be r equals 1, well, the sequence, the limits, the sequence of the partial sums, so if r is equal to 1, Sn would have been n times a, right? Because you have a plus a plus a n times, and this basically goes to, well, I should say here actually from the beginning that we are under the assumption that a is not equal to 0, because otherwise it's a trivial case. It's summation of 0, which is obviously 0. But if a is not equal to 0, obviously this doesn't go, the summation goes to, oops, sorry about that. So Sn equals Na. This will be plus minus infinity as n goes to infinity, which means, again, divergent. So the only way for the geometric series to converge is if the ratio is between minus 1 and 1. And not only we can conclude it converges, but the sum of the series is given by this nice formula a over 1 minus r. So in a nutshell, we just proved that the summation from 1 to infinity of a r to the n minus 1 is equal to a over 1 minus r if r is between minus 1 and 1, and it diverges otherwise for other values of r. So we're going to finish this lecture with a couple of examples involving this geometric series. So stay tuned for the next page. All right, so let's do a couple of examples involving this formula for the geometric series. And the exercise essentially involves using this result as a formula. So we have to do some little algebra steps to match it with the standard format, essentially to identify a and r. R is the essential piece, of course, and decide whether it is convergent or not. So here is an example. Let's say I want to figure out if the summation, let's call this example 1. So summation from 1 to infinity, 7 to the n minus 1 over 3 to the n. Is it convergent or not? Well, the first thing to do, and it will take practice, but the first thing to do is to recognize it is a geometric series. So if we use some algebra manipulation, I'm going to be able to write this in terms of a constant times another number to the power n minus 1. But I need to manipulate the terms. So notice on the top I have 7 to the n minus 1. On the bottom I have 3 to the n. So to make it to the power n minus 1, I'm going to have to take a factor of 3 separately so that I'm leaving the rest of it with 3 to the negative, 3 to the n minus 1. So you have to do a little bit of algebra steps, like I said before, to write everything in terms of some constant, which is 1 over 3 in this case, and some other constant, which is 7 over 3 in this case, to the power n minus 1. So go slow in this process to understand what we're doing here. The idea is to rewrite it in such a way that we can identify what a and r is equal to. So obviously in this case a is 1 over 3, r is 7 over 3. Because r is greater than 1, that's outside the range minus 1 and 1, hence this series is divergent. And of course with practice you could spot this from a mile ahead. Like you look at 7 to the n minus 1, 3 to the n, and you realize that with some algebra manipulations it's going to boil down to 7 over 3 to the power n minus 1, whatever. So but that 7 over 3 is the key thing. That's the ratio of the series, which being greater than 1 makes it divergent. Here's another example, same type. Let's say you have minus 2 to the n divided by 5 to the n minus 1. So because the summation starts from 1, I'm going to have to break down minus 2 to the n into minus 2 to the n minus 1. So I can combine these together into minus 2 over 5 to the n minus 1. All right, so therefore a is minus 2, the ratio is minus 2 over 5, and minus 2 over 5 does belong between minus 1 and 1. So the series is convergent. Not only it's convergent, we are in the rare case with geometric series that we can actually write down what the limit is, what the sum of the series is. So now follow the formula on the right here on the top. So a is minus 2 over 1 minus r, which is 1 minus negative 2 over 5. So that's 1 plus 2 over 5. On the bottom here, that's 7 over 5. And so that ends up being minus 10 over 7. All right. Let's see. Shall we do one more example? Another quick one. Summation from 1 to infinity. Oh yeah, that's another example that I want to... Well, actually it's this really same type, but let's do it. 5 over 2 to the n. Again, because the summation starts from 1 and the way I wrote the formula, that means I need to write it as something to the n minus 1. So I'm gonna take a 2 out. Oh yeah, what's important here, notice that the ratio is 1 over 2. Make sure it's not, don't confuse it with 2 to the n minus 1, because it's 1 over 2 to the n minus 1. So really it's like 1 over 2 to the n minus 1. So it's another convergent case. A is 5 over 2, r is 1 over 2. So it's convergent because it's between minus 1 and 1. And this will be a, which is 5 over 2 divided by 1 minus 1 over 2. 5 over 2. 1 over 1 over 2 is just times 2, so that's going to be 5. So in other cases, we have geometric series or series in general as functions. And the question is, that's a very important question, in fact, when does that function in the form of a series make sense or not? When does it converge or not? So here's an example related to the geometric series. So let's say I say you have a function to define as summation from 1 to infinity, 3, 1 minus x to the n minus 1. What's different from the previous cases is that now the ratio, so a is 3, the ratio is 1 minus x. So the question is, for what values, so for what values of x does it converge? Because in the language of functions, here the question is, does this function make sense? I mean, like, what is its domain? Can you plug in any number into the function? Just like a function, just like a square root of x, for instance, you can plug in a negative number. If the function is a series itself, it only exists insofar it's convergent, and it may not converge at all points. We know already this in general the geometric series doesn't converge to any point. But where does it converge? Well, this is a geometric series, again, with the ratio given by 1 minus x, and we know that it converges only if the ratio, that r, which in this case is going to be 1 minus x, is between minus 1 and 1. So now I can solve this inequality and provide the domain for this series of convergence. So you can solve the inequalities separately or all together if it's not that difficult. So we can subtract 1 from all sides. So minus 1 is less than minus x less than 1 minus 1. That gives me minus 2 less than minus x less than 0. And if I multiply by negative 1, that reverses the direction of the inequality. That's going to be 0 less than x less than 2. So the way you wrote this, it means that this function exists, or this is convergent only if x is between 0 and 2. So for example, if someone says, okay, I give you this function, then what is f of, let's say, let's do one example which is not too trivial. Let's say I ask what is f of 1 over 2. Okay, well, f of 1 over 2 is going to be simply summation from 1 to infinity 3, 1 minus 1 over 2, which is another 1 over 2, to n minus 1. We have the formula above, 3 over 1 minus 1 over 2, which is going to be 6. But if someone says, what is f of 5? You will say not defined. It's not in the domain of the function because the summation from 1 to infinity 3, 1 minus 5, n minus 1 is divergent. We knew that already. I mean, that's the point of finding the domain of convergence. If it's outside 0, 2, you know that it's going to diverge because that ratio won't be between minus 1 and 1. So we will go back to questions like this later to find the domain of convergence, but I think that's enough for today. So I'll see you next time.